Hello, welcome to Culture TV and to A-Level Chemistry revision. In this video we'll look at the geometry, so the shapes of molecules. This is also referred to as Vsepr Theory, and I'll show you what that stands for a bit later. In the last video we saw how to construct dot and cross or Lewis diagrams for molecules such as NH3 ammonia, and it would look like this. And we've already met the idea of structural formulae. Now it gets a bit harder when we have compounds such as carbon dioxide, whereby we can already arrange all the outermost electrons, the valence electrons, around the atoms. However, we are not following the octet rule, and to get around this problem we form a double bond, like this. This is also reflected in the structural formula, and we denote the double bond using two parallel lines like this. Now this is all relatively straightforward. Now let's move on to the more important A-level content of this topic, which involves looking at the geometry, so the shapes of molecules. And to explain why every single molecule has its very own specific shape, I'm going to start off by using ammonia NH3 as an example. So here is the molecule, and to make it a bit easier visually to understand, I'm going to show the molecule like this. First of all, we all already know, and not just from GCSE physics, but it's just common knowledge really, that opposite charges attract and alike charges repel. So if we have two electrons side by side, then they will repel each other, because they have the same charge. And exactly the same can be applicable to this scenario here, where we have a molecule, although this time we're not talking about just electrons, but rather electron pairs. And that is very important. We're talking about electron pairs. As you can see, all the electrons around nitrogen are coupled up. They're in pairs. If you're wondering why is that, well, it's to do with the fact that orbitals can occupy a maximum of 2 electrons. Yes, we saw this when we looked at electron configuration. The electrons in those orbitals also repel each other, and that is partly why they have opposite spins, but we're not interested in that at the moment because we're looking at the molecule overall. We're looking at the bigger picture. So those repulsions are ignored for now, and we're only interested in the repulsions between the electron pairs. Okay? Now, due to this repulsion, the electrons want to be as far apart from each other as physically possible. Yes? Because they have the same charge, they repel each other, they pull away from each other, and they do so in such a way that they are, in terms of distance in space, as far apart from each other as possible. They want to be isolated from each other. That is the nature of them, all because they all have the same charge. Now there's one key fact that we need to know, and that is lone pairs repel more strongly than bonded pairs. What does this mean? Well, bonded pairs are those electrons that are used to form the covalent bond. They're involved in the bond formation. They are in between, so to speak, two atoms. So in this case, we have bonded pairs of electrons between hydrogen and nitrogen atoms. Lone pairs, however, are not involved in the formation of bonds, and they are all alone, hence the name lone pairs. So they're sitting all by themselves somewhere on the valence shell of nitrogen, whatever atom it may be, and they're not taking part at all in any formation of bonds. And it just happens to be that these lone pairs, the ones that are all alone, they occupy more space and they repel more strongly. Their repulsive forces are stronger. This means that they reduce the so-called bond angle. What do we mean by that? Now, if we draw some imaginary lines through the electron pairs like this, then the angle subtended between these two lines is what we refer to as the bond angle. And quite simply, the definition is the angle between bonded pairs in 3D. Now attention, bonded pairs. So we're measuring the angle between two of their ligands. The ligands is just another term for the attached atoms to the central atom. So in this case, that's hydrogen. So really, we're looking at the angle that is formed between the nitrogen to hydrogen bond, okay? That is what we call the bond angle. Now, as you can see in ammonia, we have a lone pair. Here it is. What do lone pairs do? Yes, they repel more strongly than bonded pairs. That means they reduce the bond angle. How does this happen? Quite simply, let's just remove all this detail for now. We can now see that due to these strong repulsive forces, the other electron pairs and the atoms with them are pushed away like this. And now if we redraw the imaginary lines, we can now see that the bond angle has been reduced. That's what we mean, yes? So due to the fact that lone pairs repel more strongly than bonded pairs, the bonded pairs are pushed away from the lone pair, and the lone pair is now isolated. And due to this fact, molecules have a very specific shape, or also we can say geometry, in 3D, yes? And this shape is determined by the arrangement of the electron pairs around the nucleus of the central atom. What do we mean by arrangement? Well, quite simply, how many lone pairs are there? How many bonded pairs are there? Where are they located? That is all the arrangement. And it is this arrangement that decides what shape the whole molecule will occupy, yes? So if we know that some molecule has, for example, X amount of lone pairs and Y amount of bonded pairs, we can use the fact of lone pairs repelling more strongly than bonded pairs to determine what shape the molecule will have in 3D. To make it a bit easier for you to visualize, let's have a look at what the molecule would actually look like in 3 dimensions. It would be something like this, whereby you can see that actually the ligands, the hydrogens, are not all clumped together at the bottom, but actually they're all spread out. One hydrogen atom is actually behind, it's further away from us, and one is closer to us. Why is that? Well, we saw at the very start that electron pairs repel such that they are as far apart from each other as possible. And this is what this far apart as possible looks like. This is the only possible way that electrons can be as far apart from each other as possible, keeping in mind that they are still forming bonds. So when we say as far apart as possible, we do not mean that one electron pair is on one side of the Earth and one is on the other. No, of course not, because they are still involved in bond formation, and bonds have a certain length, don't they? Therefore, considering that fact, this is the only way that the electron pairs can be situated as far apart from each other as possible. We can also connect all the spheres like this with arrows, and that makes it even easier to see. Now, it would be quite impractical for us to draw all of this out with a 3D background as well to demonstrate what the 3D shape of the molecule would look like each time. And so chemists have devised a very specific way of showing what the molecule would look like in 3 dimensions without having to be an artist. So let's remove the background, remove the 3D spheres, and we're going to be left with the atoms. And let's just all make them the same size. We're going to have something like this. Let's return our straight line that was in the middle. And that straight line denotes that there is a bond in the plane of the paper or the screen. So if you remember back from the 3D image, the hydrogen atom in the middle was directly below the central nitrogen atom, and that is what this straight line shows. However, on the left, we have a hydrogen atom that was, if you remember, closer to us. It was larger. It was towards us. And that is denoted using a solid wedge like this. And that means that the bond is positioned out of the plane of the paper, outwards, so towards us as the viewer. And finally, on the right, we have a hydrogen atom that was further away from us. It was behind, and hence why the sphere was smaller, yes, due to perspective. And we showed that using a dotted wedge. That means that the bond is positioned into the plane of the paper. It's further away from us. So each time we draw a molecule schematically like this, we have to visualize that, okay, this hydrogen atom that's on the left is actually closer to us, and the hydrogen atom on the right is further away from us. All because the electrons that are used in the covalent bonds between the hydrogen and nitrogen atoms repel each other. And in 3D, that means that they have to be arranged in this specific way, okay? So we've looked at the 3D shape of ammonia. In the next video, in part 2, we will look at the 3D shape of other molecules and look at this in more detail. And we'll look at the Vsepr theory in more detail. By the way, that does stand for Valence Shell Electron Pair Repulsion Theory. That is exactly what we've been talking about today. Valence shell electrons, yes, those are the electrons on the outermost shell, like the ones we saw on nitrogen. Repulsion theory. So yes, basically the idea, the model, the concept of these electrons repelling each other. There we go, that's it. And that is the model that chemists use to explain the specific shape in 3D of every molecule. So to summarize then, we all know already that electron pairs are all negatively charged, and due to this they repel each other. And this repulsion causes them to spread apart from each other as far as possible. Yes, they have the same charge, they dislike each other. They want to be away from each other as far as possible, and that's why they spread out, they distribute, and they don't want to see each other at all. Lone pairs, so those are the electrons, remember, that are not involved in bond formation, they repel more strongly than bonded pairs. So therefore the number of bonded and lone pairs around the central atom and their arrangement decides what the 3D shape of the molecule will look like. Yes? So that's it for this video. Please make sure that you're happy with this summary. Please make sure that you're happy with everything in this video. If not, please ask any questions in the comments. I will definitely answer them. Thank you very much for your attention. Thank you very much for liking and subscribing. See you next time. Goodbye.